Hey guys, welcome back to the 11th episode of 12 Integrals. Hooray! And today we're going to be solving another integral again. And the integral that we're solving today looks like this. It is the integral of 1 divided by 1 plus tan x to the power of root 2, evaluated from 0 to pi over 2. So I want you to think about it for a second. And in just a second, I'll give this place back to the usual owners, and you'll see the answers to this very integral. So let's go take a look. Can I stay on for just a little bit longer? No.
I'm sorry, that was quite bad, wasn't it? Now, of course, this show is 12 integrals, so there is no way that you can solve that integral without using some little bit of a trick. Now, I will admit something. In the question, we have tan x raised to the power of square root of 2. That bit is sort of a red herring. In fact, it doesn't actually matter what tan x is raised to the power 2, as you'll see in just a second when we solve out this integral. So rather than solving out this integral that I've shown you earlier, we'll solve it for a more general case where tan x is raised to some power of a. Now this is the integral that we're going to be evaluating, and just like most of the things that we do on 12 integrals, this requires some good substitution. And the substitution that we are going to make is we are going to make the following. We are going to let y equal to pi over 2 minus x. That is the substitution that we are going to make. And from this statement, we get that dy over dx equals to minus 1, which means that dy equals to minus dx, like that. And so then we can proceed to try to make this integral look a bit better. Right, so first we could change the limits of integration, right? Because this was originally with respect to x, and so we can change it to with respect to y. That means y would equal to pi over 2 and y would equal to 0. You can check that by taking 0 and subtract and putting in place of x, and then y would equal to pi over 2 and etc. And so the next part is at dx, right? dy equals minus dx, which means that dx is minus dy. So the top is going to be minus dy. And then the bottom bit, we could replace the x with this statement, right? So it'll be 1 plus, and I'll do this, right? So it'll be tan of pi over 2 minus y to the power of a, like that. Now this next bit is sort of why this whole substitution is amazing. First, we need to work out what this bit even is. Tan of pi over 2 minus y. So I'm going to write it out here so you can see. Tan of pi over 2 minus y. Well, what we're going to do is we're going to draw a diagram first of all. So I'll draw out a simple right-angled triangle which looks like this. Now I'm going to label this angle here. I'm going to call it y, which is going to be the same y that we have earlier, right? And I'm going to say this side is, I don't know, let's call it alpha, and let's call this side beta, just like that. And you could work out what tan of y equals 2, right? It will be easily opposite, which is alpha, divided by adjacent, which is beta, and that would just equal, obviously, equal to alpha divided by beta, like that. Now, we know that all the three angles of a triangle must add up to 180 degrees, or pi radians, because 180 degrees is the same as pi radians, right? So if this is a right angle, which means it's pi over 2 radians, and this angle is y, it leaves that this angle must be pi over 2 minus y radians. And I think you can probably see where I'm going with this. So now I could try to work out tan of this angle, which is what we have here. And what this equals to is it will equal to the opposite, which is in this case beta, and the adjacent, which in this case is alpha. So equal to beta divided by alpha. And as you can see, they're reciprocals of each other. Tan y is reciprocal of tan pi over 2 minus y. So this means that this will equal to 1 over tan y. And that is the beauty of why we made this substitution that we just did. And so now I can replace that in the integral that we have earlier. So this integral will now equal to, I'll take this minus sign out, and I won't write that it's y anymore, because hopefully we figure that out. So we'll go from pi over 2 to 0 of dy divided by 1 plus 1 over tan y to the power of a.
what we can do now is we could multiply top and bottom by tan to the power of a, tan y to the power of a. Sorry, and this is just so that we can simplify the fraction that we have here. And what you will get is you will get minus pi over 2, 0. And the top you will have a tan y to the power of a dy, all divided by 1 plus tan y to the power of a, like that. Now what we can do now is, because we have a minus sign in the front, we could try to get rid of that minus sign by flipping the limits of integration. We've done this a couple of times. Hopefully you're familiar with this by now. And so we'll have the following. So tan y to the power of a dy. I hate this pencil. I need to get a new pencil. Tan y to the power of a, like that. And the last thing we're going to do is, because basically y is just a random variable, and it doesn't really matter what it is, it's not going to change the integral so much. So rather than writing it out as y, I'm going to change all the y's in this statement to be x. So I'm going to write that little note here. I'm going to make y equal to x now, which is separate from what we have earlier. And this is just changing the variable so it's easier to notice something. So now we integrate from the same limit, and I'm going to just rewrite the whole thing again like this. Maybe it's more accurate to write it that way. So these two integrals are basically just the same. All I did was I just changed all the y's into x's. They're variables, it doesn't actually matter. So basically what we have is that the original integral, which by the way I called I, is the same as this entire line here, and it will equal to this part at the end here. So what I'm going to do now is I'm going to add this to this. Right, so watch this. So 2i, because I'm going to add these two together and they're both equal to I, so it's going to be 2i, it's like I plus I, right? It will equal to the first integral, which is this integral, plus this integral here. And because both of these are integrals to the same limits and with respect to the same variable, I can combine the functions inside together. And if I combine the functions inside, well, it's just like adding fractions together, right? So that will just be, this one, obviously there's a 1 at the front, right? So this would just become 1 plus tan x to the power of a divided by 1 plus tan x to the power of a. Hopefully you see something here, dx. And then the trick here is that these two in fact cancel out because it's the same at the top and at the bottom. So this becomes simply the integral of dx, or 1 dx, from 0 to pi over 2, which easily verifiable. It is pi over 2. But remember that pi over 2 is 2i, or 2 times the original integral that we're interested in, which means that the integral that we are interested in, or I, will equal to pi over 2 divided by 2, which equals to pi over 4. And so there we have it. This integral here that we wanted to evaluate, in fact, does equal to pi over 4. And it doesn't actually matter what our power a is. And so if a equals to the square root of 2, as I set out originally, the integral will still equal to pi over 4.